the second theme, which will be linear algebra. And we are looking at it from a point of view of quantum mechanics. So the notation we're going to use is the Dirac notation, which we already saw in the introduction, but just to make sure we know what we're talking about. So we write column vectors of our complex vector space as a ket. So this is a column vector, so this will have and row vectors will be the bra, and this will be the complex conjugate of the coordinates of this row vector will be the complex conjugates of the coordinates of the column vector psi. And this is a very convenient notation for the standard inner product. So the standard inner product of, let's say, phi with psi is simply the bra ket. Okay, because naturally here we've already in this notation done the complex conjugate of the elements in the row vector. So when we do this, this is just row vector times column vector. So we just get the standard inner product on our complex space. And as we noticed before, if we write it the other way around, the ket bra, this is a matrix of rank 1. And so if I'm running out of letters. And if you apply this to say alpha, this will go to alpha, which is simply phi. Okay, because what you have here, this here, let's maybe make this big. What you have here is just some complex number. Okay, so this is just a scalar which you can move in front of your vector. Okay. So you naturally see from this, in fact, that the image is always going to be a multiple of this vector here. See, so the image is, if you matrix form, of course, is the span of the column space. So it's a very convenient notation, and we shall use it a lot. The other thing we should be absolutely obsessed with are orthonormal bases. So now this is, when you first see it, shocking to a mathematician, but I think after a while you just have to throw your arms up into the air and agree that the physicists are right, and that it really does help to use these kind of notations. So an orthonormal basis will usually be denoted with, and so we will usually denote it something like this. So again, has the property that if we take the inner product between two basis elements, then this would be 0 if they're different and 1 if they're the same. So this is the Kronecker delta that you're used to seeing. So it's a 0 if I is not equal to j and 1. Okay, so we will also use this Kronecker delta quite a lot. So that's you would have seen that before, but just to recall, that's what it is. So that's an orthonormal basis. And then with respect to such a basis, if we write, let's say, psi as the sum of CI, okay, so usually I won't write underneath what the sum is over, just because it should be, if it's obvious, then I probably won't write it. And then you see, if you simply, now we kept this with the j, so if we do j I, this would be the sum over ci j I, which will be equal to, no, we'll do this, cj, which implies that this psi is in fact the sum over. Okay, so that tells you what the coefficients are. They're simply bra I ket psi. Oh, this is fairly straightforward. From this, you start to appreciate this notation. Let's prove another fairly trivial fact. So what then happens if we look at this map? I've probably put my bracket in the wrong place there. Onto psi. Well, by linearity, this is then, which was precisely phi. So for all vectors in our vector space, we have this is this. So this implies that the sum over I of I is in fact just the identity map, which I will generally write as this kind of a one like this. And this is called the completeness relation, which we'll see again for sets of linear maps. Yeah? So we have sums of, we will have sets of linear maps where the sum of these linear maps is equal to the identity. And in this case, these are rank 1 matrices obtained from an orthonormal basis. Okay, so everything should have been fairly familiar there. That was just playing a little bit with the Dirac notation. But some things really just suddenly become a lot easier once you have this notation. For example, so this is an example where we will use this inequality at various points. So it's worth recalling. And now we can prove it in a very slick way. So this is your very, very famous Cauchy-Schwarz inequality. I know you've all seen this before, but I want to write this in using the Dirac notation. So now we're going to Juice. Oh, sorry, I don't know. Okay. So let's start off with the right-hand side here. And in here, I'm going to simply put in a sum. Since that sum there is just the identity matrix, all I've done is I've stuck an identity matrix in between here and here, which doesn't change anything. Maybe you want to write another bar here, but it doesn't need to. And the argument is that this I, this orthonormal basis, whose first element in this basis is going to be our psi, basically. So, whose first element is psi, but of course it's an orthonormal basis, so we have to normalize it. So divided by psi. Psi. And now we can take this sum out here by linearity, and we have I, psi, psi. And what we have here in this sum then is all positive, real positive numbers. Notice that this psi is a real positive number. That's just the complex. That's the complex inner product of psi with itself. And here, this is just the complex conjugate of that. Okay, so these are all real numbers, positive real numbers here. So all the terms in the sum are positive real numbers. So it's greater than or equal to the first term in the sum, which is Okay, so it's bigger than the first number in the sum because they're all positive real numbers. And there you go, that's it. Okay, so we finished. Okay, so it's worth observing that for all. So let's just observe it down here. So we will use this a lot. Yeah, so this. Yeah, this is just z times z conjugate, and this is the product of psi of itself. Right, so that was a very brief play around and just playing a little bit with the Dirac notation, and yeah, so we have to become familiar with this idea of introducing orthonormal spaces, which we will usually write as this I thing. So one thing which will be also very important will be diagonalisation. So we've already seen this in our first year course in linear algebra, but I want to go over it again because now we're going to be doing it for the spectral decomposition theorem will be absolutely fundamental. So I don't want to leave anyone behind with that. It's got to be second nature. Okay, so here goes. This is going to be 2.2. I'm going to skip over the definition of what's a linear map, understand that you already know what that is. So if I write down something like let A be an endomorphism of our complex space, I think i.e. a linear map from Cn to itself. Okay, so we're going to mainly be interested in endomorphisms of a complex vector space. As we shall see later, our complex space will be a tensor product space, but for the moment, it's easier just to do everything in general. So now, for some reason, I've used V, but let's use psi again. So just recall, so psi is an eigenvector of A with eigenvalue lambda if A psi is equal to lambda psi. And the definition of diagonalisation, A is diagonalizable if and only if there exists an orthonormal basis of Cn of eigenvectors of A. Okay, so that should be all very familiar, as should, and why is that super important?
If it's diagonalisable, then we can write in this such a case. We could write A as the sum of lambda I. It's the sum of these rank 1 matrices where this is the orthonormal basis. Eigenvectors. And this decomposition into these sum of these rank 1 matrices will be is so incredibly useful. I mean, it's suspicious that the creator of our universe really loved diagonalisation. I mean, it's just a dead giveaway. Is an orthogonal basis of eigenvectors where I has eigenvalue. Okay, so let's just prove that. So the idea is that if we calculate the sum of lambda I applied to J, then since this is an orthonormal basis, this bra I j is going to be 0, so we're just going to get, this is just going to be delta ij, so it's going to be sum over I delta ij lambda I. So this is going to be 0 unless we have I equal to j. Also, since I is an eigenvector of A with eigenvalue lambda I, let's put j here, A of j is equal to lambda jj. So that since they agree on a basis, Cn by linearity, they're the same. Well, I will. I'm going to diagonalize a couple of matrices for you. Some people like to do crosswords. Some people like to do sudokus. If I'm bored on a train journey, I'll diagonalize a matrix. So I'm going to do one of the Pauli matrices, and I expect you all to diagonalize and find a spectral decomposition for the other ones. So the idea is that to find the eigenvalues, you look at the characteristic polynomial, which is the determinant of the matrix minus t times the identity, which in this case is minus t1 minus t. So we get two eigenvalues, lambda is 1 and lambda is minus 1, and then for each one, when t is 1, you look at x minus t times the identity. You know that this matrix has rank at most 1, has rank less than or equal to n minus 1, since the determinant is 0. So it must have something in its right nucleus, which will be your eigenvector. And so 0 plus 1 is an eigenvector of x with eigenvalue 1, which we could have guessed, right, because it's just a bit flip. And t is minus 1, then we do x minus t identity is 1, 1, 1, 1, which implies that minus 1 is an eigenvector of x with eigenvalue minus 1. Now, I've just chosen a random eigenvector here. Any multiple, of course, of this vector is an eigenvalue, and this is not normalized. If I calculate the length of this vector, it's going to be square root of 2. So I have to normalize this to be able to use the spectral decomposition, because this has to be an orthonormal basis. Okay, so usually when later on we'll be doing calculations where we have to diagonalize and then use the information we get from that to calculate something, maybe in a measurement or in a Schmidt decomposition to find out the entanglement, for example. And a common mistake I make is forgetting to normalize, especially I'm just taking that. So it's always worth having it back in your mind. Did I normalize things? So according to the theorem then, it should be that x is equal to 1 over root 2. So, sorry, that was right from there. So that's the first term in the sum, and then the second term should be. Now it's going to be minus because this is the plus 1 eigenvalue, and now we've got a minus 1 eigenvalue, so it's going to be a minus 0 minus 1. Okay, so this should come all out to, this is 0, 1, right? So this is 0, 1 plus 1, 0. It's number 2. Good. Now, I don't know how much practice we have with diagonalisation, and I found that most of a lot of the time we're forced to diagonalise things with matrices which are full of complex numbers, and most of the computer packages that I use don't seem to want to do that. So I'll give you a little exercise, an extra exercise. It's not on there, so you can have a little practice because it will be worth it. So just on your own time, maybe at the end of the class, if we have some spare time, we can go through it. Try and diagonalize, find the spectral decomposition of this matrix. Okay, so just try and diagonalize this matrix, that's 9. And the ones that you still remember your first year linear algebra will say to yourself, oh look, that's a Hermitian matrix, so that's going to be diagonalized. We will talk about exactly when you can diagonalize in a moment. First we want to define precisely what is the Hermitian conjugate of a linear map. So let's consider. So this is just an example. So an exercise would be a. Let's exercise. Now, Hermitian conjugate. So let's consider the inner product between this would be well, so this I should probably have said. How would that be if we wanted to write it? We actually already saw this earlier. If we wanted to write this as this is the row vector, some linear operator on the row vector first times this psi. Okay, so this would be sorry, I forgot the conjugate. So this would be so remember that this is now a row vector being multiplied on the other side by b. So it would be the bkj. So when you've got a row vector, it's jkk, and when you multiply on the other side, when it's column vector, so it's when it's matrix column vector, it's jkk, and when it's row vector matrix, then it's jkj. So it'd be this times k. So this implies that the matrix entries here have been flipped, transposed, and then conjugated. B is a dagger. So this dagger, recall, we already defined before, but let's just say it again. And this is called the Hermitian conjugate. Okay, so in a way, actually what we have here is the coordinate-free definition of a Hermitian conjugate. Okay, so it is the map which has this property that this is equal to this.
Wait, I have a question. Why is the B on the right? Like, why is phi left multiplying B?
Here.
Like on the left. The first, yeah, here. Why is it a left multiplication?
By definition.
Like we define the map of A as, like the map by the function A or B as the right. Ah, okay, because we, like, have we already?
Yeah, what is the B such that this is equal to this?
Right.
Yeah, I see your worry. You kind of want on the other side, don't you? Right?
Like I thought that in order to get like that the Hermitian, you had to, like, they both had to be right multiplications.
Yeah. No. I mean, if you. Yeah, also, because I've also written it as BKJ, so that's just BKJ by J, which is on the other side. Actually. I think you're right.
Yes, but like when you put them inside the ket, or the one with the arrow to the left, they get flipped.
Yeah.
But like I can't see like mistake on the expression. Just seems weird to me. Like I thought, like in order to get the symmetric maps, like they both had to be, like they both have to map the vector the same way. So like they both had to be right multiplication. Like maybe I'm wrong, but that's just like that's the image I had. It just seems weird. Because phi is a column vector.
It's confusion, okay? Because this is the row vector times the B, right?
No, like isn't phi should be the column vector? Like it's like if we're doing the conjugate, like why isn't phi, like why aren't they both column vectors? Because then like we flip. Like if there were no B, right? In order to have this notation, like phi B is done before any flipping, right?
Yeah, I absolutely see. You're saying this is actually B phi ket, right?
Yeah.
And that makes sense what I've written down here as well, because what I've written down here is multiplied by the column. Yeah, PKJ, KJJ. So this is, so yeah, I think you're right. I think you're right. I mean, I copied this out of Nelson and Schwann, but I think it makes more sense to write this as this, because this is your column vector, which is then being put into a graph.
Yeah, exactly. And then you would get, yeah.
I mean, in a way, there's no chance of us being of misunderstanding this, because you cannot have this row vector with the matrix can only go in one way, right?
Yeah, exactly. Like before we had a column. Yeah, exactly. It has to be a column right multiplied or a row left multiplied.
Yeah. Okay, I think we'll go with you. Who's talking? Adrian, no?
Yeah.
Yeah, I think we'll go with your notation, right? So we're gonna go against everything in Nielsen Schwann. But I absolutely see your point. Yeah, that this is then, because I mean, I hope everyone's understanding. I mean, it's really semantics. It's really just deciding what we're going to do and stick with the convention. Because he's saying, well, he's thinking that B phi is a column vector, and then we've ketted it.
Yeah.
Sorry, graphed it. Yeah. So we've taken the ket and we've made it into a graph, which by definition is this. So I think he's right, yeah? Because this is then the definition, right? Because this is then, let me write this the other way around, it's the same thing, but BKJ phi j, you see as the matrix times the column vector, and then complex quantity.
Yeah.
Yeah, but now, hold on now. But now, yeah. Okay, well, let's leave that for the moment, and I will double check that, and we'll come back to it. Okay.
Okay.
Okay. So the Hermitian conjugate is the transposed and then conjugated, and we say if A is equal to this, then we say A is Hermitian. So Hermitian operators, matrices, will be very important for us. We're going to see various different types. I'm going to define in the next hour various different types of interesting operators for us. And at the end of the call, I'm going to draw you a Venn diagram so you can see where they all fit. Essentially, the Hermitians are to do with measurements of the quantum system, but we will go through all of that again. Some very useful observations, especially the first one, that if you sum 2 and take the Hermitian, that's the same. That's just summing the 2 Hermitians, and the product goes the other way around. Yeah, that's because of the transpose thing. So this is B. So this implies that sum of any number of Hermitian vectors. Okay, so that implies to the sum. The product isn't, yeah, so just be wary, as we already saw before. If you take, for example, are. So for examples, the Pauli matrices are Hermitian. So X and Y are Hermitian, as we saw before, and I messed it up. Because I can never remember where the minus goes with Y. I think it's that way, isn't it? I'm getting there now. XY is equal to I times Z. So we have the product of two Hermitians. So the product of two Hermitian matrices is not necessarily Hermitian. Yeah? So we have here an example where we projected together two Hermitian matrices and got one which isn't. Okay? And that's because, of course, when you do the Hermitian, you have to change the order. So you just have to find two things that don't commute. Yeah, they don't even mention this in Nielsen and Schwann. They obviously think it's far too trivial. But anyway, for me, it was worth mentioning, worth noting. So I shall write it up for you because this will get used a million times. So. So let's consider this rank 1 matrix where yeah, so how would that be then? So that would be sum over I and J, Ci, the J, and the Cj conjugate. So Ij entry in the matrix is Ci, Cj, and the Ji entry in the matrix is so this rank 1 matrix is Hermitian, whatever the psi is. So as I say, now I'm going to go through and define a whole load of other different types of matrices. Operators. So when I say matrices operators, the reason I keep repeating myself is the operator is the linear map, of course, the endomorphism, which doesn't need to be defined with respect to a basis. And the matrix is what you get when you fix a basis. Okay, so you should recall all of that. So, do we want to continue? Do you want a short break, or are everybody happy to keep marching on? I can only see Paola. You're the only one I can see. Thank you for at least keeping me company. Well, based on her reaction, I shall continue.
Wait, why is the conjugate on the J, or why was the conjugate on the J instead of the I? Like the row should be the one with, or is that not how it? I don't know. No. Yeah, no, it's fine.
No, it was right.
It was right. Yeah. It's the other. Yeah, okay, yeah. It's the opposite with before.
Because it's the wrong. You're thinking because it's the wrong way round, right?
Yeah, it was.
It's a kept round.
Yeah. Thank you.
Well, I hope you're beginning to enjoy this notation. It really is marvellous. Now, this is something else you see in your first year linear algebra course, and at some point I never really, until you start getting into quantum mechanics, really appreciate this as a tool, a way to think about, in fact, subspaces. And when we get to error correction, having worked for years in classical error correcting codes, it seems to me extremely strange that when they're describing their subspaces, they don't give you a basis for the subspace, or they don't give you a set of equations which describe the subspace. They give you a matrix, and it's the following matrix. So let's just say U is some subspace. I mean, we're always in a complex vector space, so we might as well say Cn, and let U per be its orthogonal subspace. So let's just define it. Right, so the whole space can be decomposed into the direct sum of U and its orthogonal complement, orthogonal subspace. This implies that for all vectors in our vector space, this is equal to some B of, I'll tell you what these are in a minute, where okay, so what I'm saying here, since this is a direct sum, what does that mean? That means any vector here can be written uniquely as a sum of a vector here and a vector here. And now I'm defining these as P of psi. This will be the projection, orthogonal projection of psi onto U, and this will be the orthogonal projection of psi onto the complement. And these maps, P and Q, are linear maps P is called projector. So often we will describe a subspace by just giving you its projector, which is just a linear map. Now there's some things that are worth observing here. For example, this Q, if you look at it here, it's clearly, this Q is nothing more. If I put an identity here, this is identity minus P. So this is just the identity minus P. So we have enough way of describing the complementary subspace, the orthogonal complement of the subspace in terms of its projectors. If we apply P to the projection, then this is just going to stay where it is, because if you try and write something that's in U as something in U plus something else, well, it's just going to be something in U plus 0. It's just going to be itself, because it's already in U. So this implies, these linear maps have a nice property that P squared is equal to P. So this is for all, yeah? So for all phi in this space, the projection of this is in the subspace, so therefore if I apply the projection again, it doesn't move, well then P squared minus P applied to phi is always phi for all the elements in the complex space, so therefore P squared minus P is P squared is equal to P. So with respect to an orthonormal basis, let's not, and this is another awful thing that they do, and which we will probably do as well. We're just going to write this. If we don't want to have to specify what the dimension of U is. Okay. Now this is really bad for a mathematician, because when we read this, we read a singleton subset. I read a set that's got one element in it, if I say it. So maybe we'll try and avoid that, but they do that all the time. I mean, and it's going to be difficult, so let's just make up a dimension. So R will be a random dimension. Then P is nothing more than the sum of the rank 1
And that's any orthonormal basis, right? Like it doesn't. Hello?
Yeah, any orthonormal basis for you.
Oh,
Yeah.
right.
I'm just thinking. That was. If you don't hear anything, it means I'm thinking. Yeah.
Oh yeah, no, sorry. Like I thought you couldn't hear me, like since you went to, like I couldn't see you on the camera.
No, right. Yeah. So since yeah, and again, that's just because it will agree with this will agree with P. Yeah, actually, you have to prove this. I guess you have to extend the orthonormal basis with an extend it with an orthonormal basis, with a basis for Q, so you have an orthonormal basis of the whole space, right? And then prove this. This goes to this. So since each one of these matrices, which we just proved before, is Hermitian, and the sum of Hermitians is Hermitian, the projectors are always Hermitian. Yeah, who asked the thing about any orthonormal basis?
Me.
It's you again, Adrian. Yeah, I had to quickly think there. Of course, what does p squared equal to p mean for p as a linear map? It means that the minimal polynomial is 2 squared minus t. So the eigenvalues is, well, this factorizes as t times t minus 1, so the eigenvalues are 0 and 1. So there's either the kernel, and then there's the eigenspace of eigenvalue 1. And then you just take an orthonormal basis. So yeah, there's some freedom here because you can choose an orthonormal basis. It looks like there's something special with the spectral decomposition here, but of course there is just, these are all just eigenvectors of eigenvalue 1.
It was more about how I thought it was that P is unique to the subspace.
Yeah.
And fixed, so it shouldn't depend on any choice of bases.
Right. Yeah. No. That's yeah.
Yeah. So that was it. You can pick any and they'll all be the same because P is unique for the subspace.
Yeah.
Okay. Yeah.
So so P is Hermitian. Yeah, and that's all we want to say about projectors. So now we've seen Hermitian operators and projectors. Now we're doing unitary, and then we have one more, and then I get to draw my Venn diagram, which I'm very pleased with. You can tell. So an operator U is unitary if U Hermitian U is the identity. Now, we already saw this before, and we decided this was going to be terribly important for us because U preserves the inner product. So if you have phi and psi, if U is your evolution of your quantum states, then you will be having, let's see what, so this would evolve into, so let's say, consider the so that would be now you got me worried. So where do you want me to write? You want me to write this? Right? And now if I want to move it this the other way, then I have to conjugate it, right?
Yeah, exactly. Now you get this. Yeah.
Okay. And since this is the identity, this is then. So this would be very important for us because because we need our inner product to be preserved. More than anything, what this means for us is that unit vectors go to unit vectors under U. Okay, so if you apply U to a unit vector, you get a unit vector. So somehow the probabilities, it's a valid quantum. So valid quantum state goes to a valid quantum state. Okay, I think that's all I want to say about unitary. So almost there. One more. And again, this is something in my first year in algebra course I really didn't realise was. I mean, I realised the importance in the sense of defining bilinear forms and inner products, but yeah, it's going to be fundamental for us as well. So an operator. Is positive. Now, yeah, if it's positive, then it's greater than or equal to 0. And strictly positive no, positive definite. That was the word. Damn, sorry about that. Positive definite. Yeah. So it's a positive operator just means that if you take the product of psi with a psi, then it's always going to be a positive number. Now, it's not exactly immediate, and therefore I left it as exercise to prove the following 3 statements, which I shall now say, and then it will be exercise 1. A projector is necessarily positive. A positive operator is necessarily Hermitian. And a positive operator has a has a spectral decomposition, has a diagonal representation in which all the eigenvalues are real and positive. So let me now, so that's all left as an exercise, so we're going to go through that next Tuesday probably. So let me finally draw you my Venn diagram, just so we can see where all of these different things fit. Okay, so hopefully it's going to be big enough. Here we have unitary. Here we have Hermitian. Inside here we have the positives. These ones here are the projectors. These ones here are the Paulies. And there is a grand universal set here. And this are the norm. And that is A Hermitian is equal to A Hermitian A. That is the property which unites all of these different linear operators. Okay, I'll take a short breath because now I'm going to try and prove a theorem. So kind of the first one of the day. And it's the most classical theorem in linear algebra and enormously useful for us. So all the linear operators we're going to see are going to lie on one of these sets, and this one does them all. Okay, so this applies to all of them. I think that's right. Yeah, so Pauli cannot be projector. And the Paulies have plus and minus 1 eigenvalues, yeah, so they can't be positive. Yeah, so I think so. Good. Right, so here's the theorem. Yeah, I'm saying linear operator the whole time. What I really mean, of course, is an endomorphism. Yeah, it's an endomorphism. So let's write down endomorphism because it's got to be square to make sense. And it is that if you are inside this set, you are diagonalizable, and if you're diagonalizable, you are inside the set. Right, should just about have enough time to prove this. We've got 10 average. Okay, so let's go the easy way first, which would be, let's assume that it's diagonalizable. So if it's diagonalizable, then A is equal to, by definition, lambda where formal basis. Of eigenvectors. So what we want to show is this equality. So how would a dagger be? Well, we already showed that these rank 1 matrices are Hermitian. So all that daggering does here is changes this to its complex conjugate. And now when we calculate this one, for example, we will have a sum of I, lambda I, boom, boom, plus sum of J, boom, J, boom. And because when we multiply out these brackets, this is an orthonormal basis, so the ij's will be delta ij's, we simply get lambda I, boom, I, and this is clearly the same as you're going to get if you do it the other way. Okay, it's now symmetric, in fact, in the conjugate things here. Okay, so no problem with the four-die convection. And the work is the other way. So we're going to do this by improvement. I've already defined n here as the dimension of the space. So by induction on n, for n is 1, yeah, positive operator is just this, isn't it? What have I got to show? Yeah, which is diagonalisable, right? So, well, I suppose strictly it has to be, I have to divide by the norm, don't I? So let's say A is okay, so for some unit vector psi, A is lambda times kept bra of psi, so that proves that it is diagonalisable. Okay? So n is 1. So we're going to let lambda be an eigenvalue of A. E lambda is going to be its eigenspace with eigenvalue lambda. Okay, so that consists of all the eigenvectors which have eigenvalue lambda with respect to A, and P will be the projector onto E lambda. And finally, Q will be what it was before, 1 minus P. Okay, it's the identity matrix minus P. And the idea is that we can look at this product. Now, I haven't done much at the moment because P plus Q is just the identity, okay? And now I'm going to look at these 4 terms. And our idea will be to try and prove, firstly, that these middle 2 terms are in fact 0. So let's look at PAQ. So claim, is that the easy one or is that the more difficult one? That's the more difficult one. So let's claim first that QAP is 0. So for all things in our space, B times this is in our eigenspace E lambda because P is the projector onto E lambda. So this implies that if I now go from AP, this is got to be a eigenvector with eigenvalue lambda array. This is going to be lambda times P of this. And now when I apply the Q, well, QP, I mean Q, if you think about the definition, maps all the things in P, all the things in E lambda to 0. But I mean, you can also see this as, so this is 0, but you can also see this as, if you like, this is just 0. If you wanted to add some more, there's not really much to say, because if you think of the definition of Q, it's, so we had psi is equal to P psi plus Q psi. But if psi is already in the subspace, then this isn't there. Yeah, this is 0. So this is 0. But anyway, you could write this is P minus P squared psi, which is equal to 0. It's basically the same thing. Yeah? This is P squared is equal to P. Yeah. So that one was okay. That's one of the terms dealt with. Now we're going to deal with
I'm saying that like QA is going to be in the orthogonal to E lambda, and then the columns of P are also. Could you go that way, or like you say that QA? Yeah.
I mean, yeah. When you hit the Q, when the Q hits this, it's going to take it to the orthogonal space. The P is going to take it to the other space, right?
Yes, like QA belongs to, like QA belongs to the orthogonal of E lambda, and then the columns and rows of P also belong to, or like couldn't you do it directly with, like QA is going to be like all the rows of QA is going to be orthogonal to the columns of P, or it's not that?
Yeah, absolutely. In fact, yeah, you're quite right. I mean, it's well, just think about its action on psi is always going to be 0, whatever psi is, and therefore it's a 0 map. Yeah, because this will map psi into P maps psi into E lambda and a QA. But yeah, okay, so you can do it with the columns of the matrix as well. But it's the same thing. So it's just trying to write it down in a clear way. So playing this is equal to 0. We do exactly the same thing, but now with the oh, what am I doing? Yeah. Yeah. Okay, so this implies that this vector is in the eigenspace of eigenvalue 1. Okay, because A times this is equal to lambda times this bit. And now when we apply the Q, this is then 0. which means that by But as you say, it's exactly, you could just use the argument with the columns as well. Yeah, it's clear that these two things are both 0. It's just trying to work out a fancy way to write it down. So we've got down to so this is 0, so we have this is 0. Let's just write that down. This is 0, and the Q is 0. So now we're going to have a look at PAP and QAQ. So PAP. So again, we just look at, see what happens to all the phi's, yeah? So PAP applied to phi, so this will map all phi's down into E lambda. So when we apply the A, we're going to get lambda times P phi, lambda P squared phi, which is lambda P phi, for all phi in the space. Okay, so we apply the P, we map it down into E lambda. When we apply the A, since E lambda is the eigenspace value lambda, that's just like multiplied by lambda. Lambda comes through, P squared is equal to P. So we proved that PAP is just lambda P. Okay. And finally, QAQ, we're going to prove is normal. And this is, so to do this, we need to prove that this times its conjugate, Hermitian conjugate, is the same. We can write it the other way back. Here with the A conjugate here and the A here. So first things first, using associativity of the matrices or linear operators, Q squared is Q. Now we can here QA write P plus Q because QAP is 0. Okay, so this bit here is just 0. But P plus Q is the identity, so now you see what's going to happen. A is normal, and now we have to go back the other way. So now we just do Q. And PAQ is 0 implies this is 0. In fact, that's what we proved was 0. So this is just QAQ, and now we just go back and put in the other Q. ¡Qué largo! Entonces, al final, well, what we've managed to prove is that we can just simply swap these A and the A bar. So the fact that A is normal implies QAQ is normal, if Q is a projector. So all told, what we've got therefore is that A is actually equal to lambda P plus QAQ, where this is normal. And by induction, this lambda P is just, if you think of it as a, so now we look at it. So we put together, orthonormal basis. Yeah, I mean, it's a bit ridiculous to say. I mean, I'm using induction, but of course, P on this is simply the identity anyway. So that's just taking orthonormal basis for E lambda. And then the induction part really is just taking, and then you can, just by induction, since QAQ is normal, you can find an orthonormal basis here. Yeah, because A, when you just look at E lambda per, is just QAQ. That is A. Right, this is what this table is now saying. Okay, so when we look at E lambda, A is simply lambda P. When we look at E lambda per, it's just QAQ. Apply induction, and we can diagonalize. Cool. Is that okay? Paolo's, yeah? Semi-convinced. Everybody else okay with that? So once we get down to here, just to recap, so this is now linear operators acting on very different spaces, right? So they're on a decomposition of the vector space into a direct sum. So when we look at E lambda now, so now we look at E lambda, that's A is simply lambda P, yeah, P is the identity on this space, and then on the orthogonal complement of that subspace, A is just QAQ. QAQ we proved is normal, so then therefore by induction, this diagonalizes there. Put the two things together and we managed to find an orthonormal basis of eigenvectors for A. Right. Now this is the spectral decomposition theorem. This allows us to define functions of matrices. So the decomposition for normal matrices allows us to define functions of matrices. So given a function, let's put f in. Just say, given a function f, we define f of a Yeah, I'm a little bit worried about that because it's just not really good. Well, since nobody stopped me, I shall continue, and I'll worry about my worries later. This is given that, I mean, although I've defined it as a function from complex to the complexes, but maybe it's not. Maybe the domain here is not the whole of the complex numbers. So, for example, I had some nice examples here. Yeah. You have a positive operator A, we can define the square root of A to be the sum of the square roots of lambda I. And observe that it indeed has the kind of square root property that if we multiply them together, we will get A. In fact, I mean, if you have a diagonalisation thing here, you've got the once you've got the diagonalisation, you can define any power. You know, this is the half power, but you can just put any exponent in here and it will behave exactly as you expect it to. So you can calculate all the powers of A, fractional, negative, whatever. So the exponential of A will be taking all the lambdas to the exponential, and also importantly, if A is positive definite, then we can define the log of a matrix. And that will be important to us when we get to entropy and stuff. Okay, so a positive definite. So I was looking through the exercises just to check that I'd included all the important things in the exercise, and I realized I've left one off, so I'm just going to do it as an exercise for you. Then I might start to diagonalise that matrix, because I don't really want to start with something new so near to the end of the class. So let me do this first. So I'm going to do an exercise. So I can't tell you how useful it will be to us to know that we can find the square root of a matrix. Is going to be extremely useful if it's normal, and also the logarithm. They are really going to be two extremely useful concepts. So here's an exercise. Then we can see if something is Hermitian if and only if it's got two real eigenvalues. So it's normal. So in fact, before we go forwards or backwards, we use the fact normal implies A is and if we go forwards, A is Hermitian, so A boom boom and boom boom. So the fact that this is Hermitian and all of these things are Hermitian and the sums of Hermitian is Hermitian, and these things are linearly independent. Implies that lambda I is equal to lambda I conjugate for all I, so A has real eigenvalues. And going back the other way, I is immediate, right? I mean, so since, yeah. That was in fact immediate. Okay, so that's probably why I didn't include it as an exercise. I probably thought that was too easy. But even though it's easy, it's important to realize. Okay, just because the exercise is easy doesn't mean it's not important. Okay, so that we can spot the Hermitian ones because they're the ones that have got real eigenvalues. So if we see a spectral decomposition here and all these numbers are real, we're going, okay. If it's not, then it's not Hermitian. So as I say, next time we're going to start with tensor products, and then we have to look at traces, and yeah, there's still a little bit to do, which is probably going to take us most of Thursday. So we can expect to start. I will then assign the exercises, which we expect to do probably on Tuesday. So let me just do this in the last 10 minutes. You can either listen or not listen. I will attempt to, or start to anyway, diagonalize this following matrix. So the idea is always the same. The recipe is always the same. So you want to so this thing is Hermitian, so it should diagonalize with real eigenvalues. So the characteristic polynomial of this thing needs to be calculated, and these things look horrendous, and you don't want to do it. So you have to kind of look for, hopefully whoever wrote the exercise did something nice and allowed us to. So I think here the idea was, if I sum I times the third column here, that doesn't change the determinant. So the determinant, you can always sum multiples of a column of a column and multiples of a row to a row without changing them.
Did we use the minus t on the 3?
Sorry?
Like on the diagonal, like on the 3.
Oh yeah, thanks. I would have noticed. Thank you. If I multiply by I here, I'm going to get a 1, right? So if I then multiply by I and sum it, that can't be right. If I multiply by I. Oh yes, if I multiply by I and sum it to the first one, then I get 2 minus t, 0, 3i minus I, which would be 2i minus an it. Here I get 5 minus t, I minus I, 3 minus t. Now you can see, when you're a mathematician, they don't let you diagonalise matrices because they think it's too beneath you. So I know I remember going through the entire linear algebra class when I was at university, which was an awful long time ago, and I shared a house with a guy who was doing chemistry, and he was also studying linear algebra. And I looked at his homework, and all he had to do was like diagonalise matrices, and I was like, that's just too easy. That's not fair. That's what we've got to actually do it. And it occurred to me that they never asked us to actually do it. So once you get your first factor out, things tend to get decidedly easier, because now you can use these things and clear things up a little bit. So I guess I'm going to take away I times the first row to the last row and get a 0 here, and I've got a 1, 0, 0, and things get a little easier. So I minus a minus I is 2i, 3 minus I squared is going to be 4, maybe. Oh dear, I did it differently then. Left my cheat sheet. Right, I'm on my own. Don't panic. So now we can just do this 2 by 2, can't we? That hard now. 2t squared minus 9t, 20 minus 2. And these look like nice numbers, right? So somebody's been kind. 2 minus t, t minus 6, t minus 3. And then once you've got yours, then things then you get your chance to check. So when t is 2 and you look at a minus t times the identity, you should find that this is a rank 2. And I'm guessing that this is a scalar multiple, isn't it? No. Yes. Yes, it's I times that. So I0 minus 1 is an eigenvector. And you have to go through the other ones. Okay, so t is 3. How are we doing for time? Well, I've almost finished. Okay, so you do the other 2, and then a will be, so this will give you one term in the sum, So the eigenvalue is 2. And also here, now you have to be careful here because it's I0 minus 1 times, so this is like your rank 1 matrix, okay? Plus the other two terms. Okay, so I'll leave you to calculate those for the T is 3 and T is 6. So this was our 2, but here we have to normalize, and this is a bit hard to forget. So you have to divide by what's the length of this vector has length square root of 2, and this one 2. So we have divided by square root of 2 squared. So this is actually going to just cancel this. And then you add up the other 2. Okay, so, and you can, I'll leave the rest of that for you, and you can check that in the end you should get that matrix there. Okay? And as I say, sometimes we will be trying to, I don't know, for example, calculate the Schmidt decomposition of a quantum state. And to do that, at some point you have to find the spectral decomposition of one of the matrices. And then, yeah, I don't know, unless somebody can find a nice computer package to do it. Otherwise, I have to do it by hand. I mean, I've got 2 or 3 which will do it if everything's real. But as soon as there's a complex number there, then they just like, oh. So I don't know. Anyway, as I say, I'll dish out the exercises on Thursday, on Tuesday, sorry, and then next Thursday. Oh, then we'll only have 2 exercises, 2 days. Well, maybe what we'll do is, because I'm not going to do it yet because we have got lots still to do, and most of it won't make any sense. You can have a look at it; it's already there if you want to. So probably what we'll do, I thought it was Tuesday today, I shall stop filming for the start. It's making me nervous now. Now remember they're still filming. Ah! Let me